Hi, I'm Dongliang from the University of Bonn. This is joint work with Florian Bernard. Our ECCV paper is called Hypernetwork Neural Functional Maps for Unsupervised, Robust 3D Shape Matching. We want dense correspondences between two non-rigid 3D shapes, every point on one surface matched to a point on the other. On clean synthetic data, this is largely solved. On real scans, it is not. Real data comes with topological noise, where surfaces that should stay separate fuse together, and with partiality, where large pieces of the shape are simply missing. Both distort the intrinsic geometry of the surface, and intrinsic geometry is exactly what functional map methods are built on. So let me recall what a functional map is. Instead of matching points directly, we describe each shape by the first k eigenfunctions of its Laplace-Beltrami operator, its spectral basis. A correspondence then becomes a small k by k matrix C that maps one basis to the other. That matrix is linear, and that is the whole problem. When a shape loses a leg, or when two surfaces fuse together, the eigenfunctions do not simply get scaled and mixed. They deform in a way that no single matrix can undo. You can see it here. Matching through the standard functional map leaves the bases misaligned at the red arrows. The information is present in the bases. The linear map just cannot express the correction. Our fix is to stop insisting that the map be a matrix. We replace it with a neural functional map, a small 3-layer perceptron acting on the spectral coefficients with a skip connection that carries the standard functional map straight through. Two things are worth noticing. First, when the nonlinear residual goes to 0, we recover the classical functional map exactly. So this generalizes the framework rather than replacing it. Second, the network operates on k-dimensional spectral coefficients, not on the mesh itself, so it stays very cheap. But where do these weights come from? Optimizing a separate network for every shape pair would be slow, and it would need a good initial correspondence to optimize against in the first place. Instead, we predict the weights with a hypernetwork. The pipeline has 3 stages. First, a standard deep functional map block gives us an initial linear map C, together with a soft correspondence matrix Pi. Second, the hypernetwork reads C and outputs the weights of the neural functional map. Third, we push the source basis through that network and read off correspondences by nearest neighbor, search in the realigned spectral domain. The hypernetwork itself is a vision transformer. The trick is to treat the k by k functional map as a single channel image and to have the transformer output 3 channels, one for each linear layer of the neural functional map. Self-attention matters here because the structure that reveals how the shapes are distorted is global. Partiality, for example, leaves a characteristic slanted diagonal across the whole matrix. And all of this trains without any ground truth correspondence. The loss simply asks the neural functional map to agree with the soft correspondence from the first stage. Transport the target basis through pi, warp the source basis through the network, and minimize the difference. On to results. TopKids is the standard benchmark for topological noise. Children in various poses where the arms fuse into the torso. We cut the mean geodesic error from 9.2 down to 6.7. That is the best result on this dataset, and notably better than methods such as smooth shells or deep shells, which additionally rely on extrinsic spatial information. We stay purely intrinsic. On partial matching, the gap is larger. On Shuri-C, 16 holes, we reach 4.7 against 9.7 for the unsupervised baseline. On PFOST hard, 2.3 against 5.2. What we find most telling is the comparison with supervised methods. Our unsupervised model is ahead of supervised DPFM on both of the hardest splits, and the module drops into existing pipelines unchanged. These numbers come from adding it to 2 different frameworks. So, the takeaway. A functional map does not have to be a matrix. Letting a hypernetwork predict a small nonlinear map, trained with no ground truth correspondence, is enough to fix the spectral misalignment that breaks linear functional maps under partiality and topological noise. Please come by our poster in Malmö. Thanks for watching.